Have you ever questioned the nature of your reality? What if everything you believed is up for debate in the quantum realm? Welcome, fellow explorers of the unknown, to a journey into a universe smaller than an atom, yet vast enough to challenge our fundamental understanding of reality. We're talking about the realm of quantum mechanics, a branch of physics that studies the behavior of particles at the quantum level, where the rules of physics as we know them seem to break down. Imagine a world where a particle can be in two places at once, where it can spin in opposite directions simultaneously, and where its state can be entangled with that of another particle, light years away. This is the world of quantum mechanics, a world that seems to exist beyond our everyday experience and comprehension. Quantum mechanics was born in the early 20th century, when scientists like Max Planck and Albert Einstein began exploring the behavior of light. It was a revolutionary idea, challenging the classical physics of Newton. And while quantum mechanics has since been proven to be incredibly accurate, predicting phenomena with astonishing precision, it continues to baffle even the brightest minds. In essence, quantum mechanics tells us that at the microscopic level, reality is fuzzy. Particles exist in a state of uncertainty or superposition until they are observed. Suddenly, our solid, predictable universe seems less concrete. But why should we care about this quantum weirdness? Well, the answer is simple. Every piece of technology you use, from your smartphone to your computer, from medical imaging to GPS, relies on the principles of quantum mechanics. It's the foundation of modern technology, and its potential is virtually limitless. But as we delve deeper into the quantum realm, we're not just unearthing new technological possibilities, we're also challenging our understanding of the universe and our place within it. We're questioning the very nature of reality. So buckle up as we dive into the mind-bending world of quantum mechanics. Imagine a cat that's both dead and alive at the same time. Sounds impossible, right? Welcome to quantum superposition. In the realm of quantum mechanics, there's a concept that's as baffling as it is intriguing. It's called quantum superposition, and it's all about the idea of being in two states at once. Sounds like something straight out of a sci-fi movie, doesn't it? Let's delve into this concept a bit more. To do that, we'll turn to one of the most famous thought experiments in quantum physics, Schrödinger's cat. Picture this. A cat is placed inside a sealed box with a radioactive source, a Geiger counter, and a vial of poison. The Geiger counter is set up so that if it detects radioactivity, it will break the vial, releasing the poison and killing the cat. The radioactive source has a 50-50 chance of emitting a particle within a set period of time. Now here's the kicker. Until we open the box to check, we can't know if the radioactive source has emitted a particle or not. Therefore, we can't know whether the vial has been broken and whether the cat is dead or alive. According to the principles of quantum mechanics, the cat is both dead and alive at the same time. It's in a superposition of states, but the moment we open the box, something strange happens. The cat is either dead or it's alive. The act of observing forces the cat to choose one state. This is what we refer to as the collapse of the wave function. It's a mind-bending concept, isn't it? Yet it's a fundamental part of quantum mechanics. This idea of superposition, of things being in two states at once, is not just confined to the atomic level. It has implications for the whole universe, for our understanding of reality itself. This paradox is just the beginning of how quantum mechanics challenges our understanding of reality. Imagine two particles miles apart behaving as if they are one. This isn't science fiction, it's quantum entanglement. In the surreal realm of quantum mechanics, particles can become entangled. This means that two or more particles can become so intimately connected that they effectively lose their individuality. It's as if they become one entity, sharing a single existence. Consider this. You have a pair of entangled particles and you take one and shoot it off into space while the other stays here on Earth. Now, if you measure a property of your earthbound particle, like its spin, you instantly know the spin of its entangled partner light years away. Now you might be thinking, so the particles are just like two synchronized swimmers, right? They've somehow agreed in advance to match each other's moves. But it's not that simple. If it were, it wouldn't have troubled the likes of Albert Einstein. The reality is, until you make that measurement, your particle can be in a superposition of states, spinning both up and down at the same time. But the moment you measure it, it snaps out of this superposition and takes on a definite state. And the moment it does, its distant partner does the same instantly, no matter how far apart they are. This is where things get really spooky. You see, this instantaneous action seems to defy the universal speed limit set by light. According to Einstein's theory of relativity, nothing can travel faster than light. Yet the information about the state of our particle seems to have done just that. This phenomenon is so strange and counterintuitive that it stumped even Einstein. He wasn't a fan of quantum mechanics' probabilistic nature, and he really didn't like entanglement. He called it spooky action at a distance. So there you have it. Quantum entanglement, where two particles become inextricably linked and the state of one can instantly affect the other, no matter the distance between them. It's a mind-bending concept, another testament to the weirdness of the quantum world. Einstein called it spooky action at a distance, and it's another way quantum mechanics defies our everyday understanding of how the world works. Does a tree falling in the forest make a sound if no one is there to hear it? In the quantum world, it might not even fall at all. Welcome to the curious realm of the observer effect, a theory that has left us questioning the very fabric of reality. In our everyday lives, we are accustomed to the idea that things exist whether we observe them or not. The sun still shines even when we close our eyes, and the Earth continues its orbit whether we're awake or asleep. But dive into the world of the infinitesimally tiny, and this familiar concept starts to unravel. The observer effect in quantum mechanics proposes that the act of observation can alter the outcome of a quantum event. It's as if the universe is saying, I won't decide until you look. Imagine flipping a coin. In the quantum realm, this coin is both heads and tails at the same time until someone observes it. Only then does it collapse into one definite state. But how can this be? How can our mere act of observation influence reality? Some suggest it's due to what's known as wave function collapse. The quantum system exists in multiple states represented by a wave function, but observing it forces the system to collapse to a single state. Others suggest it's not about the observer, but the act of measurement itself. When we measure something, we're interacting with it, physically disturbing it in a way that could change the outcome. So it's not so much about us seeing it, but more about touching it. It's a conundrum that has sparked endless debates. And while we may not have all the answers, it's clear that the quantum world operates on rules vastly different from our everyday reality. So, the next time you're contemplating whether a tree makes a sound in the forest, remember that in the quantum realm, that tree might be both standing and fallen until someone decides to take a look. It seems in the quantum world, observation plays a crucial role in determining reality. So, what does all this mean for our understanding of reality? We've delved into the mind-bending world of quantum mechanics, where particles can exist in multiple states at once, connect over vast distances, and seemingly alter their behavior when observed. Let's recap. Quantum superposition, for instance, tells us that a particle can be in multiple places at once. It's akin to being in New York and Tokyo simultaneously. This concept, illustrated by Schrödinger's famous thought experiment involving a cat that's both alive and dead, defies our everyday experience and challenges our understanding of reality. Then we have quantum entanglement, or as Einstein so eloquently put it, spooky action at a distance. This phenomenon allows particles to become intertwined in such a way that the state of one instantaneously affects the other, no matter the distance between them. This defies our conventional understanding of cause and effect and challenges the very notion of locality. We also touched upon the observer effect, a peculiar aspect of quantum mechanics where the act of observation influences the observed. It's as if the universe is saying, I'll decide what I'm doing once you look at me. It's an idea that turns our understanding of objective reality on its head. All of this paints a picture of a world that's much different from the one we're used to. A world where the objective reality we thought we knew, influenced by cause and effect, is replaced by a fuzzy, interconnected, and observer-dependent reality. Quantum mechanics invites us into a realm that's strange, counterintuitive, and downright bizarre. It's a realm where particles can be in two places at once, where action at a distance is a reality, and where the observer and the observed are inextricably linked. Quantum mechanics asks us to accept the strange, the counterintuitive, and the downright bizarre. It challenges us to rethink what we believe about the very nature of reality itself.